Recording in progress.
Hello, everyone. Welcome to today's Nest Talk. And today I'm very pleased to have Chen Liu to give his presentation about reasoning within the mind, dynamic multimodal interleaving in latent space. We know nowadays it's a very popular topic to scale reasoning, not only as language, but also in like vision or video space. So let's have a listening for Chen Zhi's presentation about how he proposed this dynamic pattern to have language and vision syncing together. Now let me give a brief introduction to Chen Zhi. Chen Zhi is a first-year PhD student at University of California, Santa Barbara, Department of Computer Science. His research interest lies in trustworthy AI and the algorithmic foundations of multimodal large models, with a focus on enhancing their reasoning capabilities, reliability, and interpretability across diverse input modality. And I'm today's host, I'm Da Wei, and I'm currently a second-year PhD student at Arizona State University, and my research focus is large language model and data mining. Now, Chen Zhi, could you share the screen and start the presentation?
Okay, I will share my screen. Can you see the screen?
Yes.
Okay. Hey everyone, my name is Chen Zhi, from the Computer Science Department at UC Santa Barbara. Today I will talk about multimodal reasonings. Okay, so in the first part, I will briefly discuss the key challenges in multimodal reasonings, as well as recent progress in this field. And in the second part, I will introduce recent papers of our lab, which studies central questions in multimodal reasonings. How can we make multimodals, vision language models in a more human-like ways? So instead of following fixed reasoning steps or heavily relying on external toys, we ask whether models can use its internal signals to dynamically adjust its reasoning process and decide when it needs to look back at visual information. So, families, I will talk with you about future directions in multimodals and latent reasoning. So, for the first part, let's talk about the recent progress in multimodal reasoning. Since last year's RL learning, especially methods such as GRPOs, has become increasingly popular from training large language models. This trend has quickly extended to multimodal reasoning models as well. Many recent papers have adopted GRPOs or SFT-style trainings to teach multimodal reasonings to perform reasoning process, often in the forms of step-by-step reasoning chains. On this slide, I have posted some classical papers doing this parents, which generate some explicit reasoning process. However, as the communities continued to push reasoning's performance higher and higher, important questions naturally emerged. As multimodals becomes better at reasoning, do these also become better at visual perceptions? So in our works last year's present in Europe, we take a closer look at these questions. Since it was an early stage studies, we focus on evaluating servers models available at that time. I have shown the visualizations results in the slide. You can see a very consistent patterns emerge in these results is that although these models demonstrate strong reasoning performance, their virtual projections abilities does not always improve. And in some cases, it's even worse than that of the base models, like Queen 2.5. So this led to important takeaways. Multimodal reasoning models should not focus only on improving reasoning performance, but also have to keep balances between reasoning and perceptions. So in the next slide, we have investigate these questions. We first evaluate varieties of multimodal reasoning models, multiple visual perceptions benchmarks, such as hallucinations benchmarks and MMVP. We observe consistent patterns across these models. Their hallucinations become more serious as reasoning abilities improve. Instead, as models become better at solving problems through reasoning, they may rely less on visual evidence, which can lead to more serious hallucinations. And one interesting thing is that under the experiment setting at that time, model trainings purely with IOs tend to show better perception performance than those trained with SFTs. We have shown the result here. We can see that for different perceptions benchmarks, only IR training models has a better accuracies than the SFTs plus IOS models. One possible explanations is that IR trains reasoning chains are typically shorter and more complex, and therefore less influenced by stronger language pairs, which helps present visual groundings. I will also discuss these observations in more details in the next slide. And it is worth noting that these observations comes from an early stage of multimodal reasoning models development. As training algorithms like GRPOs have evolved, and as model scales and data qualities have improved, the relative performance of iOS-only models and SFT plus iOS models is no longer a straightforward comparisons. But anyways, we believe that this observation was particularly meaningful in the early stage of studying how to train this multimodal reasoning model, as it highlights potential problems between explicit reasoning and visual perceptions. So as we have known, there has these problems of the reasoning models has a large hallucinations in perception tasks. So we want to explore why cause these situations. So we use very classical and wide use methods, which attention visualizations to analyze these situations. So we can first say that the first visualizations we have compares reasoning models and no reasoning models on perception focus tasks. In this attention maps, we use MMVP benchmarks and visualize their layer-wise attention distributions over visual tokens and task token. So from these comparisons, we observe a clear and consistent patterns. We can see from these two diagrams, for the no reason models, Queen 2.5 Rails models has a larger vision tokens attention than the R11 visions, which is reasoning models trained by GRPOs. So we found that reasoning models attend significantly less to visual information than non-reasoning models. So this suggests that language pairs are amplified once reasoning process is introduced. So once we identify this stronger reliance on language pairs, a natural follow-up question is whether it is related to the length of the explicit reasoning process. So to study this, we analyze models' behaviors under different thinking modes. For the second figures, we have tried two settings. The first one is we let the model have normal thinkings, which only use the prompt controls. And we found that in this case, the models has a large attention to the image tokens. But however, if we let the models to generate a long reasoning process, which we call overthinking settings, we found that the attentions to the image tokens has a decrease. And for the instruction tokens, which means the text-based tokens, which has a higher attention. So we found for these findings, it shows that longer reasoning process are associated with weaker reliance on visual information. So based on above findings, we further control the reasoning length of different models using three strategies. I have listed the thinking length controls methods here. The first one is tokens baggage forces. So what this means? We let the models to reasonings on a fixed reasoning process. We use the prompt controls to let the models, for example, only generate 500 reasoning tokens. And for the second methods, we have used the test time scaling, which we remove the end thinking special tokens and let the model to generate over and over again to have a very long thinking. And the last methods, we have introduced latent-space steering methods to control the length. For specifically, we first define the long repetitions and the short repetitions, which we define thresholds like 500 tokens for long reasoning process, and for maybe less than 100 thinking tokens as short repetitions. And we have got two repetitions, and we can do this process to get the directions. So the directions is the latent space to control the models to generate the thinking process. So we can use these directions to control it to generate more thinking length or less thinking length. So for these three methods, we have got the results in this visualization. These results suggest that reasoning length performance first improves as the thinking length increased. And as the thinking length, for examples, increased to 400 tokens, the performance will have a degradation. So this results suggest that reasoning length plays a critical role in both reasoning and perceptions. A moderate amount of reasoning helps the models better understand the task, while long thinking process tend to be negative, affect visual perception. So these observations has also released a key message of our work. In multimodal reasonings, improving reasoning should not come at the cost of the capabilities of perceptions. And achieving strong performance requires a careful balance between reasoning and perception. So for these ideas, we have studied the balances between reasonings and perceptions in the vision language reasoning models. We first built a small benchmark that evaluate this trade-off in a most controlled settings, where perceptions and reasonings are strictly decoupled in our benchmark. And actually, we also define a matrix similar to AOCs, which you can see for here, where we have construct X and Y visualizations. The X shows perceptions and the Y represents reasonings. By controlling the length of the reasoning process, we can get a curve that's showing the trade-off between reasonings and perceptions. The area under these curves showing how well a model balance these two abilities. And on these benchmarks, we have also observed some trends that match our earlier results. For example, large models tend to have keep a more stable balances between reasonings and perceptions. For example, for the three different scikit-length control settings, we can see that the 7B scales models has a more RHAOC accuracy than the 3B models. And the third one is that the models trainings only with IOs usually produce shorter and more concise reasonings, whilst models trainings with supervised SFTs, supervised fine-tunings, followed by IOs, shows longer and more complex reasonings. We also have shown a case study for here to compare these two different training paradigms. And more importantly, these benchmarks have shown a new insight. Having more training data alone does not guarantee a good reasonings and perceptions balances. And instead, how relevant the data is to the task and how good the data qualities matters much more. So following our discussions on the balances between reasonings and perceptions in multimodal fields, many recent works have begun to explicitly study these issues. In particular, they place greater emphasis on visual perceptions during RL learnings, aim to prevent perceptions for degradations as reasonings becomes very longer or stronger. So one line of works as shown in the left of the slide. This works explicitly identifies tokens that are strongly related to visual perceptions during reasonings. It has doing a random mask process to let the models to focus to say the image. So if the reasoning chain is very long, the models also have to use these pairs of image to do the perceptions and reasonings. And during the training process, this works also applies stronger learning signals to these visual dependence tokens, encouraging the models to pay more attention to visual information when doing the reasoning process. And another similar works goes a step further by modeling the dynamic relationships between reasonings and perceptions. It separates reasonings relate tokens from perceptions relate tokens during the reasoning process. And the dynamics reweight these two types of tokens at different stage. You can understand, you can see this method as they have found which tokens is target or relate to the reasoning's abilities, and which tokens which is related to the perceptions, and the dynamics to change the weight in the RL trainings to achieve the balances. So this allows the models to better balance the perceptions and reasonings. And in addition, another line of works aim to improve multimodal reasonings by restructuring the reasoning process itself. You can see the right side of this slide, which focus the models to first performance visual perceptions and only doing this process to carry out reasonings with the goals of strengthening perceptions groundings before reasonings begins. And a related but most fine-grained approach examines the reasoning process step by step. You can see for the left, these methods identified visual tokens that are most relevant to each individual's reasoning step and requires the models to reply on these tokens at each step, ensuring that every step of reasoning is grounded in visual evidence. For examples, you can say for this case studies, this works has each explicit reasoning steps to integrate with the corresponding visual part. So overall, well, this line of works can improve both reasoning and perception to some extent, but most of these methods they operate primarily in the language space and relies on explicit or hand-designed training methods, which maybe reduce models' flexibilities and can hurt generalizations, especially in more complex or open-end situations. So following these paradigms we discussed earlier, since around April of last year, one topic that has attracted significant attentions in the communities is which called thinking with image. So the core ideas of these directions is to enhance visual localizations and perceptions by allowing the models to use visual toys during reasoning process. For example, the two papers I list for here have both used IO learnings to train models to activities called visual toys, such as zones and bounding box, in order to better localize relevant visual regions and improves visual perceptions. However, this approach also introduces several notable challenges. The first one is that visual toys use is often unsuitable. The models does not always call the right toys at the right time. And second, this method typically requires large GPU resources and large-scale training data, making them expensive to train and deploy. And finally, interleaving textual reasonings with frequently visual operations significantly reduce inference efficiencies and the scaled abilities. So building on this direction, some works recently explores agents or toy-based frameworks where visual information is first hovered into semantic representations using some external toys or agents, and then feedback to the models for reasonings. This designs can improve reasoning efficiencies and making trainees more scalable. But however, since these frameworks introduce an external agent or toys to perform this process, so they do not fundamentally change the model's internal reasonings and perceptions mechanisms. So in addition, Think with Image has recently expanded into several new paradigms. For example, I will share some recently very popular papers for here. Some methods introduce a visual step into the reasoning process that generates image, writing lines, or diagrams through code. You can see the right of this slide. For the reasoning process, it has one part is that the models has generated the visualizations code and to get the visuals information. So this approach does not rely on calling external toys to get the information of perceptions. But one important thing is that the models creates the code maybe it's not unsuitable, and maybe it cannot generalize to most complex situations. And another methods I have talked about is that it uses some generate methods to generate intermediate visuals that support multi-step reasonings. Similarly, in some unified models, the models performs textual reasonings while generating visual content, which provide additional evidence to guide the reasoning process. But overall, although these methods can improve multimodal reasoning to some extent, whether through visual toys or generations-based approach, this still fundamentally relies on explicit visuals and textual representations during reasoning process. So for these situations, the models is required to reason step by step over explicitly present visuals and language content. But for a human's behaviors, this process is quite different from which we think about some questions. When humans reason over image, we do not explicitly write every virtuals or text elements. Instead, much of the reasoning happens implicitly within in our mind, right? So these observations have naturally led to the growing interest in multimodals in latent space. Recently, several projects have explored whether multimodals reasonings can integrate information directly in latent space without relying on explicit visuals or textual outputs. For example, for the papers showing here is one of the earliest work that argues for these paradigms and analyze existing frameworks from a latent space perspective. Its training strategies is relatively simple. It restricts where implicit reasonings can happen by phasing specific token positions. By doing this, the models is encouraged to encode visual informations into latent representations that better match the semantic structures need for correct reasoning. And also, these papers are similar with this slide I have taught, so I was now to discuss more. So far, I have outlined reasons programs in multimodal reasonings. This overview was intended to classify the current research landscapes and the case challenges that this field remains. So maybe this is maybe a long overviews of these papers. So with these backgrounds, I will next introduce the motivations and the methods of our works. As we have all seen that existing approach not only textual only reasonings and sync with image, we have talked about there have servers from many limitations. So this leads to natural and boredom fractions, convention language models, interleaving reasoning and perceptions in a way that is closer to human behaviors. So to explore these questions, we follow on two specific research questions. The first one is whether models requires visual perceptions at every step of the reasoning process. And the second one is if not, can internal models representation signals when visual perceptions is actually necessary. So for the first questions, we firstly defined visual dependence scores, and which is designed to measure how much the models relies on visual information when generating particular tokens. So basically, we feed the models with original image and noise versions of the image, and compare the model's predictions from the same tokens positions under these two inputs. A larger difference between the two predictions indicates that the tokens is more dependent on visual information. So as shown in the figure 2, we visualize the result at both the token levels and the reasoning chains levels. For these distributions, we observe that only a very small numbers of tokens strongly depends on the visual information. And this sparsity is also consistent at the levels of entire reasoning chains. And one interesting thing is that we also found that as visual dependence increased, the overall reasoning accuracies become higher, which you can see for these figures, for the red lines, as the reasoning chains most depends on the visual tokens, it will has improvements of accuracies in the reasoning performance. So for this analysis, we have got two observations. The first one is visual reliance during reasoning is sparse and highly uneven across tokens. And the second is reasoning chains with stronger visual reliance consistently achieve higher accuracies. And in addition, to address the second research questions, we further investigate the impact of the internal confidence on multimodal reasonings. We first introduced a matrix called confidence gains to measure how much each reasoning step contributes during step-by-step reasoning. It is defined as a change in the model's probabilities of the correct answers after adding a reasoning step. So a higher confidence gains mean that the step increases the model's confidence in the correct answer. So as shown in the left figures trace, we can find that correct reasoning chains consistently exhibits higher confidence than those that lead to incorrect answers. And when we analyze confidence at the levels of individuals' reasoning steps, we found a similar result. These false reasoning steps tend to have higher confidence, while hallucination steps are associated with lower confidence. And in addition, we have exams confidence in the pure visual perception task for the MMVP benchmark that compares hallucinations tokens with no hallucination token. The results from the figure 4 show that hallucinations tokens generally have lower confidence and weaker reliance on visual information. So together, these findings suggest that internal confidence serves as a meaningful signal that it is closer related to both reasoning faithfuls and visual groundings during multimodal reasoning. So based on the all analysis and findings, we summarize three key takeaways. The first one is that higher confidence is generally associated with higher reasoning accuracy. And the takeaway two, confidence reflects the qualities and faithfulness of the reasoning chains. And the last one is higher confidence is also aligned with stronger visual groundings. It is worth noting that these relationships are not strictly positive correlates, but instead exhibit a certain degrees of correlations. So these findings allows us to clearly define the goals of our works. Rather than modify models parameters, we formulate the problems as a test times optimization task. As with the models weight fixed, we model the reasoning process step by step and aim to adjust the model's internal latent thinking representation. Our objectives is to minimize the model's overall confidence when reasonings over giving textuals and visual input. This encourages the generation process to move toward more stable, consistent, and reliable reasoning behavior. So with these observations in the mind, we now introduce our methods. You can see for these pictures, which we introduce our frameworks that which called dynamics multimodal latent reasoning. Our approach consists of two core components. The first one is test time optimizations in latent space. And the second is dynamic visual information injection. Let's first talk about the test times optimization, which first introduce a small numbers of sync tokens at the input stage, which serves as an internal space for the models to perform reasoning. These sync tokens are embedding together with the test tokens and image tokens and are then intuitively optimized during inference. So based on our earliest analysis, we have found that internal confidence is a reliable indicators of reasoning qualities. So we use confidence as a reward functions for here to guide the test time optimizations of these sync tokens. So we adopt policies, ratings, basis latent space optimization strategies, directly updating the sync tokens in the latent space. While similar ideas has been explored in some works on latent space optimizations for large language models, such as latent sync methods. But our work's focus is on multimodal settings, where reasonings must integrate both visuals and textual information. So to encourage explorations and avoid whole low-cost optimizations, we applied a small noise to the sync tokens before optimizations begins. It has shown here equations 5 in our papers. And but there has released one very important problem is that only optimize the thinking tokens introduce potential risks. If confidence is the only optimization signals, the models may reinforce its own beliefs and becomes overconfident in some incorrect answers, which maybe cause the hallucination. So to address this issue, we introduce visual informations as an external constraint, allowing perception to help direct the reasoning path. So unlike previous methods that inject visual informations in a static or one-shot manners, often based only on attention scores, we argue that visual information should be dynamic, inject based on the model's current reasoning state. So we begins by inject a fixed numbers of visual tokens. Slide use top case attention strategies. These visual tokens are then jointly optimized with the think tokens during the test time inference for hairs. If the overall confidence increased after these joint optimizations, the inject visual tokens are considered helpful and are added to a best visual patch pool, which stored visual tokens that have consistently provide positive contribution. This pose is continually refined throughout inference. In subsequent loads, if injecting new visual tokens does not improve confidence, we do not update the pose and instead continues to use previously slide visual tokens that have already showing benefits for the model's reasonings. So in this way, virtual information is injected only when what is consistent provide reward, rather than relying only on highest attention regions. And in our experiments, we have found that the best visual patch pose can converge to a stable state during the optimization, which showing that only a limited numbers of visual tokens can truly benefit for the overall reasoning process. And for this slide, we have shown our methods with some several training-free styles approach. One point that is important to classifiers is we do not directly we do not compare DMLRs with training space latent space methods. Such approach typically relies on large-scale initial trainings, which naturally lead to significant performance gains. Our methods, however, operate under different settings. Specifically, DMLRs requires no additional trainings. Instead, it relies only on the model's internal signals to perform self-evolving iterative refinements at test time. And as a result, while DMLRs consistently improve performance, the overall benefits are not extremely large. We view that there is not as limitations, but as indications of promising directions for future works, particularly towards more systematic self-evolving learnings in latent space. And beyond accuracies, we also compare with the inference efficiencies of different training phrase methods. For instance, approach such as ICOTs, which involves multiple rounds of interleaved vision language reasoning, tend to encourage higher inference costs and lower efficiency. But in contrast, DMLRs introduce only a small numbers of sync tokens at initializations and use a dynamic visual injection strategies, allowing it to manage strong reasoning performance while keeping inference times relatively low. So this slide also mainly presents as analysis of how servers' parameters affect the performance of our methods. From the first figures, we can see that increase the numbers of optimizations iterations generally lead to performance environments. However, we also observe that too many iterations does not necessarily brings additional benefit, because in practice, a moderate numbers of iterations is enough to achieve notable improvements. And besides that, we also examine the impact of servers' other factors, such as the numbers of visual token inject and the amount of noise added to the tokens and the numbers of latency tokens. Each of these parameters influence performance to different extents. One important observation is that different models can be sensitive to these parameters. We also found that results may have some change across different machines or hardware setups. So this behavior is not unique to our methods and has been widely reported in some works on self-syncing and LLM's latent space reasoning. So these findings point to an important directions for future research, developing more stable and robust latent space optimization methods that generalize across models and environments. And finally, I would like to briefly discuss some futures, directions, and open questions. I think one promising directions for the latent reasoning is to extend the training paradigm to generations models, especially for vision language actions tasks. Because these tasks relies heavily on visual input and often require repeatedly processing high-dimensional visual information during both reasonings and perception. This can introduce significant efficiencies and compute bottlenecks. So recently, an increased numbers of papers have begun to explore VRA settings in latent space, which making this particularly timely direction. And another open questions considers that the training paradigm itself. Most existing latent space methods mainly focus on learning continuous visual tokens, while visuals and task informations are stored models in separate space. this with natural corrections, can we design a more unified latent space that more naturally integrate visuals and textual informations for joint modeling and reasoning? So this is all for my talk. So if you have some, if you are like to discuss these ideas or other related topics, feel free to reach out. I will be happy to chat more. And so thank you for your attention for our project. And so the next time we give to David.
Yeah, thanks Chenzhi for this very interesting paper. And now, if you have any question, feel free to share it with us, and we will discuss it together with Chenzhi. And let me see. Okay, I think we have a question about what is the specific structure and content of cross-modal representation?
Uh, I think this is a very general question, so I don't sure which is talk about for the different paradigms. So uh, I have list as we have talked about for this slide, we have I have shared three different multimodal reasonings patterns for here. The first one is the textual only reasonings, and the second one is sync with image methods, and the latent space reasoning methods. So I think these are three classical structures for cross models representation. Yeah. Maybe,
Yeah, I
maybe the questions can be asked detailed.
yeah.
Yeah. Okay.
So I think it's a good summarization about the three type of like multimodal latent reasoning paradigm. And
Yeah.
yeah, let me see. Okay, so maybe here I can ask a quite general question about latent reasoning or latent space reasoning. So to me, I think there are basically two benefits of using COT or having COT when we do the reasoning or do the inference. The first one is, of course, it could improve the final accuracy of the response. And the second one is in some like decision-making process, we want to know what is the internal like intermediate reasoning process or how model make the final decision, especially in some high-stake scenario like healthcare or education. So if we consider the problem from these two perspectives, so I think maybe some latent space reasoning method could improve the accuracy, of course. But I think it also somehow reduce this explainability to make it not transparent to like users or researchers to understand. So do we have any specific method or like if we can address this problem in from a multimodal perspective?
Yes, I think this is a very good questions. For the latent space reasonings, as you have said, the one bottleneck is that we don't know the models how thinkings and doing the process in the latent space. And recently, I have seen papers for large language models doing latent space learnings. It has doing one thing is that doing the latent space learnings, it first let the models to learn how to generate the latent space tokens. And it has also parallel training methods is that it's decoding the latent space tokens and to generate the response to say, so in this way, it can say that the models, how the models trainings and how the models thinkings on the latent space. Yeah. And actually, I have shared papers here for these papers. It also use decoders to decoding the visual token for hairs. For example, as I have said, it has used these frameworks in different tasks like navigations, understandings. So it can use the decode models or something like this to decoding the visuals information like pictures to know how the model's perceptions or reasoning. So I think maybe in the futures, we can also do a spiral trainings, which we first let the models to learn how to generate latents, repetitions, and also we have to make sure that the latents repetitions is we want, or it's have to uh, look at the right regions in the pictures. Yeah.
Yeah. I think it's really interesting to have a read about the paper you mentioned. Yeah, I think it's just try to achieve a balance between the like faithfulness and effectiveness. And for our previous question, here is the clarification. So basically, the audience is interested about basically the type of content of the cross-modal information. For example, is that embedding, or is that like some kind of token?
Yeah. In our methods, uh, we have generated the final response. You can see there are two stage. For the first stage A, we have only iterate, optimize the think token and the visual token together to let the think tokens uh, uh, most stronger. And next, as we, for example, iterate 5 times, and we will choose the best reward as the best think tokens, and it will generate and decoding the final answers. So it will has a explicit output generation. Yeah.
Yeah, I see. Uh, okay, there is another question about that. Can the entropy be used for every single video?
Uh, I think it maybe it may talk about the confidence signals or entropy. Yeah. Because we have used confidence to get the multimodal reasonings. I think entropies is also a very useful toys to get multimodals to do some tasks like videos or embodied stuff. Yes. But I have not tried, but I think it is makes sense.
I see. I think the question might be about confidence, not entropy. Yeah. And
Yeah, okay.
yeah, go ahead.
I think that there are two similar matrices because empties is when um entropies and confidence. I think they are showing one's journals repetitions of the models. So I think uh these two signals can also guide the model's behaviors.
Yeah.
Yeah.
Thanks for this insights. And uh, okay, I think another question from me is basically in that paper you use confidence as a kind of signal, right, during the inference time. And I also read some paper about like use confidence as a supervision signal during training or as a basically proxy of models like self-estimation, right, during inference time. And some work will mention that this type of method using confidence as a proxy will lead to some collapse. For example, if you use it to train the model, then the model maybe will be overconfident at the end of the training. So do you have any this type of question when using this confidence as a proxy metric?
Yeah, yes, I think using confidence as internal signals to guide the our trainings is a very promising direction. And for our papers, I have released one problems for only use the confidence is that if the models only is optimized by the confidence reward, the models maybe only cares about to get a highest reward of the confidence. So it may be lead to a situation that we don't want, is that the models is very confident to generate wrong answers for this. So in our works, we want to avoid the situation. So we inject some visual tokens to let the models to look back to the pictures and to make the reasoning process more stable. Yes, and we have say to only use confidence as a reward to iterated optimization. Sometimes it can have a little improvement, but sometimes it may be decrease the overall model's reasoning performance. So I think uh, maybe using in the IO trainings or SFTs is makes sense than for the test time. Yeah, because in test times we usually face some problem in that is not stable. Yeah.
I see, I see. So basically, maybe when we want to use confidence as a signal during inference time, we need to be careful, right? Maybe it's not
Yeah.
that easy as we use it during training time.
Yeah.
That makes sense. And here we have another question about basically the token use in different stage. So only in the second phrase or phrase B, we use the language model token. In phrase A, do we only use visual tokens?
For this part,
Yeah, I think
yeah,
we have
the
different phrase, right? Yeah,
the purple colors here is image tokens. So we have used image tokens after the embedding layers and integrate with the sync tokens to do the optimization process.
I see.
Uh,
Yeah, I
and
think,
we have do the dynamics visual information injection for here. Not we inject all the visual tokens to the latent-space.
yeah, I think that's very clear. Yeah. And okay, I think we still have time maybe for one question. So if you have any question, please feel free to share with us. Okay, I don't see any new question from our audience. And yeah, thanks again for Chenzhi. And I think it's a very interesting talk about latent space reasoning. And look forward to maybe more work from you in the future. Yeah, thanks. And I think that's pretty much
Okay,
about today's presentation. Thank you for watching.
thank you.